I would like to welcome Adam from the Westfälische Wilhelms University of Münster. Please go ahead.
Thank you, Tim, and thank you for the invitation to speak here in this nice conference. So today I'd like to tell you about some new interactions that are happening between the theory of random walks and theory of C-star algebras, which are certain kind of Banach algebras. So let's start with some background on random walks. What is a random walk? I want to be completely functional theoretic here somehow. So suppose that I have a countable group and a finitely supported probability measure on the group. And this group is discrete, right? So a random walk on G is just a stochastic matrix. And it is given, its entries are given by the following formula. So it's a G by G stochastic matrix. And we will assume throughout that the support of this measure generates the group as a semigroup, and that the support is finite, kind of like a Cayley graph construction, perhaps, with a finite set of generators for your group. And we will denote by EP the collection of edges in this graph on the set of group elements that is given by the following formula. So it's only the graph for which there exists some probability to move from one edge, from one vertex or one group element to the other. Right, graph. So here we have our first example of what a random walk is. So suppose we take our group to be the integers to the D, and we assign a probability of 1 over 2D for each direction. So for instance, if you imagine this in the two-dimensional situation, then you have a probability of a fourth to go either north, south, east, or west. And this is called a simple random walk on the integers to the D. And I want you to notice that if this measure of ours is symmetric to begin with, somehow then the matrix itself, this P, stochastic matrix, is itself also symmetric. So that means that it's equal to its transpose. Okay, and so we would like to take iterations of this matrix or iterations of this process, if you like, and we will denote by PGH to the bracketed n, the GH entry of the nth iterate, which is also the same as the following convolution. So suppose P, I want to talk a little bit about recurrence and other analytic properties of random walks. So I will say that P is recurrent if the sum of all the probabilities to move from G to H in n steps diverges for some or all G and H. And I want to define the spectral radius of the random walk to be the following limb sup, okay, which is the same. If it exists for one, then it is the same for all others. All other choices of the G and H. So clearly, when P is recurrent, then we get that the spectral radius is equal to 1, right? Because you can think of this as a formula that expresses the radius of convergence of some power series, right? And then this tells you that this radius has to be equal to 1. And then a theorem of Polio and a converse by Varopoulos says the following. So this is very classic. It says essentially the following. It says that if you have a drunkard walking on the plane in this simple random walk on the two-dimensional space, then the probability that it returns to a particular position, that it visits a particular position, no matter where it starts, is equal to 1. So it's always going to come back to the same position again and again. So it's recurrent. But if you, God forbid, talk about a drunkard bird, right, moving in three-dimensional space with probability an eighth to go in each direction in three-dimensional space, then the bird is only expected to visit a particular position finitely many times. Okay, so we would be mostly interested in random walks that are transient, so that for any finite patch of the group, the walker sort of leaves that finite patch forever, and it sort of goes to infinity. And so here's an example of something that's highly transient. So this is the free group on D generators. And you attribute the probability of 1/2 to the D for each generator or its inverse. And this is called the simple random walk on the free group. And another thing that's related to the spectral radius is this notion of amenability of the group. So this means that you have a left invariant mean on L infinity functions on the group. This is the same, actually, it's a theorem of Kesten from 59. It's the same as having some or any symmetric random walk on the group with spectral radius equal to 1. Okay, so for instance, for this free group, we know it's not amenable, so the spectral radius is not going to be equal to 1. I think this is also one of the ways you can show that the free group is non-amenable. So another property that I'd like to focus on today is this property of a strong ratio limit. And what does this property mean? It means that the ratio between transition probabilities sort of converges if you take the same iterations. So this property has been studied by many people over the years, in going back to Eresh and Chang even. It has been shown by Margulis to be satisfied for nilpotent groups, by Avez for symmetric amenable random walks, and on the free groups by Lally, and more recently for symmetric random walks on hyperbolic group by Gossel. So this is sort of the background on these random walks. What can I say about operator algebras or C-star algebras that I can generate from them? So here is a construction that we apply. So suppose that I have a random walk on a group, the way that I had described. I'm going to take the following Hilbert space. So I'm looking at all the m length paths in this graph on which my walker sort of goes on. And I look at a square summable sequences over these paths, and I look at all iterations. This is my Hilbert space, and it has the following nice parameterization for an orthonormal basis for it, which is EHK to the m. So HK is an edge in the mth iteration of my graph or my matrix. And I look at all possible iterations. Of course, P to the 0 is just the identity matrix. And then for any GH, which is, has a positive probability of going from G to H in n steps, in this n, we define a sort of analog of a shift operator. This is SGH to the n, and it does the following. It acts kind of like matrix multiplication here. You see, I get delta function, which is 1 if n h prime 0 otherwise. It's sort of like a matrix multiplication together with shifting. I'm starting at the mth component, I'm moving it to the n plus mth component together with some weightage. And this weightage is nothing other than a conditional probability. Okay, it's the probability of going from, it's going through the vertex H at the nth step, conditioned on starting at G and ending at K at the n plus mth step. So this is a way of encoding a random walking operators. And then what we do is we bunch them up together. We look at the norm closed, adjoint closed, Banach algebra generated by these operators on this Hilbert space. And this is called the Toeplitz algebra. And it encodes some information, a lot of information, in fact, on these random walks, particularly this notion of a ratio limit that or related to this ratio limits that we've mentioned previously. Okay, so but in fact, this construction doesn't arise from nothing. It's actually a construction due to Arveson and Shalit and Solel. They apply, so they sort of describe a general procedure of taking an operator semigroup on some C-star algebra or von Neumann algebra, and then apply this construction, and you get this Toeplitz algebra. This is called the subproduct system construction. And I want you to notice that by definition of these operators, this Hilbert subspace, so suppose you fix your K, right? And you let H and M vary according to these parameters, then you get a reducing subspace. Why is that? Because you start with somebody that's in the subspace and you stay in it, right? You see, I didn't change the kth entry, and the same is true for the adjoint of this operator as well. So this is a reducing subspace. So that's for understanding some of the quotients of this Toeplitz Banach algebra or C-star algebra. Okay, so from spatial consideration, we have our first collection of symmetries of this operator algebra, and this is something that you can do. Given a sort of creation operator, or maybe I should say a weighted shift operator here, you can always multiply it by z to the n if it comes from this particular n. And this turns out to extend to point norm continuous action of the unit circle on this Toeplitz algebra. This is sometimes called the gauge action, in analogy to perhaps the gauge action on Fock space. So a little bit of history. In his paper, Ami Wieselter, gives an example of a natural Toeplitz quotient C-star algebra coming from this construction that I previously mentioned, which is not T-simple. What does that mean to be T-simple? It means that it is not the smallest equivariant T quotient of the Toeplitz algebra. So this is a natural example, but sort of fails to be the smallest T-symmetric quotient of this Toeplitz algebra that we talked about. Instead of this, he asks if his class of what he calls Kunz-Pimsner C-star algebras are symmetry simple in some sense. And if you have it for this gauge action, this is sometimes called the gauge invariant uniqueness theorem. So this is something that's very useful for studying these C-star algebras and their representation theory. Okay. So now there is a difference that one has to make, between having a unique smallest T-symmetric quotient or T-symmetric quotient. So these things are not equivalent. This is Wieselter's example. And in a slightly different context that has to do with more non-commutative geometry context, there was a paper of Arici and Kant where they consider additional symmetries on these Toeplitz algebras in a related context. They have these SU2 actions on Toeplitz algebras arising from irreducible representations of this Lie group. And they sort of observed that if you add these additional symmetries, this problem of Wieselter goes away. So his natural examples somehow are the smallest SU2 symmetric quotients. So the idea here is perhaps we didn't look at enough symmetries when we were trying to find the smallest symmetric quotient of our Banach algebra. Okay. So let's try to shed some light on this question of Wieselter. So, yes. So suppose I have this Toeplitz algebra that I defined. There is an additional action coming from the group, the way that we had defined things. So suppose I have an element of the group X, I can simply multiply it with G and H from the left. So this is kind of like a left multiplication action of the group on itself. And this gives me another action that sort of commutes with the previous action of the unit circle. Oops, okay. So here's our theorem. Suppose we have a hyperbolic group and a symmetric random walk on it. Then there is a unique symmetric quotient with the following collection of symmetries. This is the collection. It's the group times the unit circle. But it is a proper quotient of the natural Wieselter Kunz-Pimsner C-star algebra. So this sort of perhaps answers his question in some way, because it tells you that, well, you add a natural collection of symmetries and still it has to be a proper quotient of Wieselter's algebra while still being a unique symmetric quotient. So there is a unique symmetric quotient. It's just not always this one that Wieselter defines. However, in this context of Arici and Kant, there is a recent paper of Neshveyev saying that Wieselter's algebra are in fact the right object in this SU2 symmetric situation. Okay. So how would I go about proving something like that? How long do I have now, actually, if I may ask?
You have 10 minutes.
Over 10. Okay, 10 so that's plenty of time. Okay. So let's try and explain some of the details of the proof, okay, and what goes in from the theory of random walks as well as some other things. So here is the definition on G, and I denote by the following J, G nu, the ideal. So I take the Toeplitz algebra and I intersect it. So remember, these HPKs were reducing subspaces, so I can always look at the collection of operators such that they are diagonal, block diagonal, according to indexing through the group G, and each block has a compact operator on each one of the reducing subspaces. So that may not be a subalgebra or an ideal, but if you intersect it, then it is an ideal. If you intersect it with the C-star algebra, it's an ideal. And then the Kuhn C-star algebra, I define it to be the quotient by this ideal. If you want to draw a comparison with the algebra that Wieselter defines, the direct product, he looks at the C0 summing operator. So imagine that I mentioned we had a block diagonal big matrix indexed by G, such that each block has a compact operator. Imagine that these compact operators go in norm to 0. That's the definition that Wieselter gave for his ideal. So this here would be a further quotient, possibly. We still haven't gotten to the properness of the quotient, but this is potentially a proper quotient of the C-star algebra that Wieselter defined. Okay, so how did we come up with these ratio? How do we compute this algebra? So this goes back to the theory of random walks. So suppose we have a random walk, and we denote by H the following ratio limit kernel. So this is with this strong ratio limit property. So I assume these exist. And the ratio limit radical is the largest subgroup of elements for which these ratio limit functions hxy is equal to hxe for every x. So you run over all x's and you only take those y's that satisfy this equation. And then the ratio limit space is the smallest compactification of this quotient space, which makes these functions extend continuously. This you can always do in general. And the ratio limit boundary is then the set difference between these things. And it's a closed subset. Okay, so the beautiful thing about this, that this definition is entirely a definition in the theory of random walks. And it came about from trying to compute quotients of these Toeplitz C-star algebras. So from the studying of these Toeplitz C-star algebras, we get new and about random walks. So here is our theorem, really. Suppose you have a random walk with a strong ratio limit property so that these ratios converge. Then the Kuhn's algebra that I defined is continuous functions on the ratio limit space times the unit circle, tensored with compact operators on L2 functions on G. And in fact, if this ratio limit boundary is non-trivial and the action of G on it is minimal, then the unique symmetric quotient for this collection of symmetries is a further quotient of this algebra. So if you look at the algebra that I defined, you need to take even a further quotient for it to be the unique smallest symmetric quotient with this collection of symmetries. Okay, so how do we apply this theorem to get the one that I previously mentioned? This is appealing to work of Wolfgang Boas, who is a person in the theory of random walks and probability. He showed in a paper that was written at the same time as my own, in a coordinated effort, that for symmetric random walks on hyperbolic groups, the ratio limit boundary coincides with Gromov boundary of the hyperbolic group. And because the action of a hyperbolic group on its Gromov boundary is always minimal, then this satisfies the conditions of my theorem, and thereby giving us a lot of examples that have a unique symmetric quotient for this new collection of symmetries and are proper quotients to the C-star algebra that Wieselter defined in great generality. So some concluding remarks. So we see that studying Toeplitz quotient C-star algebras for random walks lets us discover new canonical spaces and boundaries for random walks that have not been considered before. Using the behaviors of transition probabilities, we have many examples of unique symmetric quotients for Toeplitz algebras for random walks. And this leads us to natural questions about the theory of random walks. So somehow the studying of operator algebras associated to random walks then motivates questions back in the theory of random walks. So does every random walk have the strong ratio limit property? This is still not known. Is the group action on the ratio limit boundary always minimal? I don't know. I mean, it's just been invented. We just discovered this, right? So we still have lots of questions, but at least we were able to shed some light on this question of Wisselter, and we're hoping to make further progress on these questions. Thank you for your attention.
Thank you very much for your talk. So are there any questions? Or comments? Okay, if not, again, thank you very much for the talk. And
Thank you.
I think